we go. That's the way. So hopefully you'll enjoy tonight's lecture. It's over to you, Dan.
Great. Thank you very much for that introduction, Brian. And thank you also for joining us on this evening's sixth lecture. But I'd also like to say happy birthday to the West Yorkshire chapter of the IMechE as well. I understand it's 100 years old this week, Brian. So congratulations to all you guys.
Yeah, thank you.
So as we've mentioned, moving forward, today's presentation is on the subject of steam quality. And this follows on from the previous 5 presentations that we've gone through, where hopefully we're starting to get a good understanding of both the fundamentals of steam, the basic design considerations, and how we use it. So today's presentation should really start to pull together to give you a greater understanding how all of those things can have an impact for whoever it may be that could be involved with actually using the steam. As far as steam using sites are concerned, that could be a quality engineer, it could be a production engineer, it could even be a health and safety manager. So we've made the introductions previously. It's really just to remind you of the purpose and the value of moving forwards and downloading that useful little app that we've spoken about, that's available for download for your iPhone, for your Android phone, free of charge. Please download it, as that will make life very, very easy for you whenever you may be involved in engineering a steam system, regardless of whether you're actually away from your desk or in the plant room itself. So as we've mentioned, today's presentation, steam quality. And we're going to look at a few basic design considerations. We're going to look at a few different standards, but most importantly, we're going to consider what steam quality actually means to those of us that are using steam systems. So one of the first things I want to refer to is what we call the steam quality triangle. And this really shows us an understanding with regards to how and where different conditions of steam are used. So in previous presentations, we've spoken about plant steam. And when we're talking about plant steam, typically it's steam that is going to be used in heavier industries or for applications where the process or the atmosphere isn't likely to be contaminated with anything that could be carried in the steam. So a perfect example would be whenever we're using steam for heat exchange purposes, for the provision of domestic hot water or heating. We know that a little bit of scale or rust, or if the steam is slightly wet, we know that it's not ideal, but it's not going to cause too many major issues for the client. However, if we're using that steam for direct injection purposes, for example, it could be in the pharmaceutical sector, it could be for humidification in a hospital operating theatre, it could be for sterilization purposes across a number of different sectors, or it could be for directly injecting into a baby food jar for sterilization purposes, or to pull a vacuum on the lid. Whenever we're using steam for direct injection purposes, then of course it becomes critical that we're not injecting excess moisture in with the steam. It also becomes critical that we don't have a carryover of boiler chemicals from the boiler into the process. It also becomes critical to understand that we don't want any scale or any rust conveyed into that process or atmosphere. So when that happens, we need to move up the steam condition triangle and ensure that it's treated in some way appropriately, or maybe generated completely differently. And I'm going to come on and talk about the steam condition triangle in a little bit more detail as we go through the presentation. So moving forwards, we've already discussed the basic properties and the fundamentals of steam on our previous presentations. We know that steam's a gas, we know it's compressible, we know there's a direct pressure temperature relationship, we know there's a lot of energy in it. I could labour the point further, but hopefully you've grasped the basics through those previous presentations you may hopefully have attended. And similarly, we've looked at the steam tables and the temperature enthalpy curve previously. That helps us to determine the operating pressure of the steam, the boiling point of the water, the point at which steam starts to be produced, the volume that the steam has when the mass of water is being evaporated, and the energy content of the steam. What I really want to focus on is that temperature enthalpy curve. Because what you'll remember from previous presentations is that this really demonstrates the journey that water takes as it starts to evaporate and produce steam. So we know that if the fuel is contaminated in any way, we know if our client
going to be a cat.
We know if we know if our client isn't generating steam efficiently, we know that we're likely to end up with steam that is neither dry nor saturated with energy. So that can cause two problems. First of all, if the steam doesn't have sufficient energy contained within it, then we're going to have a delay at which the energy can enter the process. But if we've got wet steam, it brings us a number of different issues. We've mentioned previously, wet steam is more likely to condense out in the distribution pipework. That could in turn result in a little bit of corrosion of sensitive areas like steam traps or the pipework itself. So of course, if we've got corroding pipework, we could have rust entrained within the steam that is conveyed towards the heat exchanger. But if we're using that steam for direct injection purposes, not only are we going to have that moisture entering that atmosphere or that product, we'll have rust entering the product as well. We also know that wet steam can result in erosion of sensitive areas. For example, if we've got an eroding control valve, it makes it nigh on impossible to control the flow of steam onto the process accurately. We also know we're likely to get those water hammer issues, health and safety issues that we've spoken about. But we also know that we're highly likely to have a reduced mass of steam finding its way to the process. So all of these issues that we encounter with steam that isn't generated in a dry and saturated condition can result in a poor condition of steam finding its way to the process. And again, we've spoken previously with regards to the pressure to volume and the pressure to temperature relationship. And these have really got the basis in the steam tables. But the steam tables are based on the understanding that the condition of the steam that we're working with is fully dry and saturated. In other words, it's an excellent condition. But if we've got very wet steam with a lot of moisture contained within it, first of all, it means that wet steam is going to have a different density to dry steam. So that pressure to volume relationship is slightly askew. And we've already mentioned that if we've got wet steam, we can't rely on that temperature to pressure relationship in exactly the same way that we could if we had dry saturated steam. So you can see that the process conditions can be slightly misaligned unless we've got that excellent condition of steam. So what does that mean for our client who's using steam? Well, it basically means that if we're talking to any number of different stakeholders on our client's site, if we ask them what steam condition or steam quality means to them, steam condition and steam quality will mean different things to different people. And it really comes down to what we're actually using that steam for. For example, if we're talking to an engineer that's working at an oil refinery, for example, good condition of steam basically means that he's getting the correct mass flow of steam to the process at the correct pressure. It's reasonably dry and there isn't an excess of particulate within it. But if we ask an engineer that's working in a pharmaceutical process or a food and beverage factory, or if he's working in a hospital, if we ask him about steam quality, then he's going to want to ensure that his process or atmosphere is protected. He's going to want to ensure that he gets the correct mass of steam to satisfy the process. He's going to want to ensure that he's got the correct pressure and temperature of steam. He's going to want to know that the steam is as dry as it possibly can be for a number of reasons. First of all, the drier the steam, the more energy present within the steam. but the drier the steam, the less likely it is that we're going to be contaminating that process or atmosphere with an excess of water. And remember, that water, it's not going to be potable water. We will have added a number of different boiler chemicals to it to make it suitable for generation within a plant steam boiler. But it also means that we can have an excess of air and non-condensable gases. We can have rust, and we can have scale, which is again a dried out concentration of boiler chemicals. All of these things could be contaminating the steam and enter the product or the atmosphere. So if we ask an engineer that is using steam for direct injection into the process about steam quality, he's going to want to measure it. He's going to need to know exactly what it is we're talking about when we refer to steam quality. And there's the standard that we refer to as BS-EN 285 that we use to benchmark the condition of the steam. So whenever we're using steam for direct injection, good quality steam means that it will be 95% dry or better. That way we know how much energy there is within the steam, and we know that there's going to be very little moisture, if any, entering that process. We also want to ensure that we've got less than 3.5% of a condensed sample of steam, which has an air and non-condensable gas value. So less than 3.5% by volume. Why? Well, we know from previous presentations that a presence of air and other non-condensable gases, that's a barrier to heat exchange. So it can cause the process to slow down, or it can fail to let us heat the process up to the required set point altogether. And of course, it means we're going to want the process to be protected from particulate, such as that rust or the dried out boiler scale that we've spoken about. So when we're talking to steam quality, we need to understand what the client's requirements are. Closed loop system, very simply, we want dry steam with little particulate in it, but the requirements are going to be far greater if we're moving towards a more sophisticated process. So just going back to the beginning again, the very first presentation that we went through all those months ago now looked at how we generated steam in the boiler house. So if we require an excellent condition of steam at the process, we're never going to get that unless we're generating an excellent condition of steam in the boiler house. And all of those components that we've discussed previously that are shown on the screen in blue, the boiler feed tank, a little bit of heat recovery, level control probes, blow down valves, they're all involved with ensuring that steam is generated safely, that steam's generated efficiently and reliably. But as far as this presentation is concerned, it's to ensure that the steam is generated at the best possible condition we can. If we're not generating steam with a view to keeping the condition as high as possible, then we're never going to get a good condition of steam at the process. It's as easy as that. But we can actually take it one step further backwards from the boiler center, and that's to understand that the quality of water that we use, that is going to impact how we actually treat the water in the boiler house, which will in turn impact upon the chemical and mineral composition of the steam as it travels to the process. So apologies for those of you that maybe you're dialing in from outside of England or Wales. The map that you can see, it really shows the feed water or the raw water quality in England and Wales. And given that this presentation has been arranged by the West Yorkshire chapter of IMechE, you can see we're in quite an unfortunate area because we're at a crossroads of three different raw water qualities. So you can appreciate that if we travel 20 miles in one direction, then the water quality can get better or it can get substantially worse. It all comes down to the raw water and where we're obtaining that water from. We could be using river water, borehole water, reclaimed water, or it can be coming straight from the mains. But even if that water is coming from the mains, there's no guarantee that the local water authority is going to be drawing from a reservoir in one part of the region or in a different part altogether. So it's critically important that we routinely monitor the raw water quality and ensure that not only are the dosing pumps working correctly, but the water treatment regime is correctly aligned. It's a science in itself. And the purpose of the the purpose of the water treatment is principally to ensure that we're keeping the water as soft as we possibly can, and to ensure that we're getting rid of as many oxygen and non-condensable gas particles. So once we've treated the water in the primary water treatment, then the water goes into the atmospheric feed tank or the hot well. And hopefully you remember from previous presentations, we've mentioned that condensate, well, it's already been chemically treated. So condensate is an excellent condition for being recovered back to the feed tank. The more condensate we recover, the less raw water we need to consume. And the less raw water we need to consume, the fewer the chemicals we need to add to the feed tank. But it's inevitable. We are going to have some condensate losses. So we will need to bring in some raw water. So we'll need to add a few water treatments, chemicals into the feed tank itself, just to polish off that last remaining presence of any air and non-condensable gases. Remember, air and non-condensable gases, if they enter the boiler, that's going to be the primary cause of corrosion in the boiler itself. So we can check the temperature gauge on the side of the feed tank. The closer that temperature gauge is sitting to 85 degrees, then it's an indication that not only are we generating steam efficiently from an energy perspective, if we're putting hot water in the boiler, we can generate steam quickly. We can generate it with relatively little input of energy compared to putting a lower temperature of feed water straight into the boiler. So if the temperature gauge is hanging at 60 degrees as opposed to 85, it's an indication that not only is there an energy inefficiency, but that we're likely to be consuming far, far more chemicals because there's going to be more oxygen that needs polishing off before it enters the boiler itself. And again, what I hope you'll remember from the previous presentation is that the boiler level controls, the purpose is to maintain the water level within the boiler so that it can keep up to steam production. It can trigger an alarm if the water level rises to a dangerously high or a dangerously low point, but it can also send a signal to a feed pump. Now that feed pump can either be an on-off pump or it can be a modulating pump. The benefit of moving away from an on-off pump to a modulating pump is that when the feed pump switches on at a low level, and when it switches off, when it reaches a high level, the band of relatively cold water that could be added to the boiler can be quite large. So you'll know yourself, if you pour a pint of cold water into a pan of boiling water, the boiling rate falls off, and then we've got to wait for that pan to start boiling again. And it's at that point when we've got the steam that's recondensing and then taking on more energy, it's that point that we get wet steam being produced. And what you remember from previous presentations is wet steam being drawn into the distribution pipework. That's what's going to contribute to the erosion, the corrosion, the water hammer. That's what's going to contribute to the steam having less energy contained within it than we were otherwise expecting. That's going to impact on the process. So if we move towards a modulating pump, then that's the equivalent of just drip feeding in a very, very small mass of boiling water from a kettle into that pan. It basically means that we're not at risk of the boiling flattening off, and therefore we're not at risk of getting wet steam. With a modulating pump, we get steam that is generated not only more efficiently and more consistently, but it's going to be routinely of a much, much higher quality. Now, the boiler level controls, they can either be magnetic floats, they can be conductivity or capacitance probes. If we want to move away from an on-off control to a modulating control feed pump, we need to be using the capacitance level control probes. The good news is that both the level control probes themselves and the feed pumps can be very, very easily be retrofitted to an existing boiler with very little modification required. So if you ever are working on a process and you're concerned that the steam condition isn't at the point where it should be, then the very first thing we should be doing is heading back to the boiler house and examining the way that the steam is actually being generated. Simply changing the level controls and the pumps out can have a hugely beneficial effect. But we also spoke about the blowdown that we need to perform within the boiler. And that's because the chemicals and minerals present in the raw water and the chemicals and minerals that we add to the raw water itself are going to behave in two different ways. So think about having a cup of tea at home. If you put a spoon of sand and a spoon of sugar into your cup of tea, well, the sugar would dissolve and the sand would just sink straight to the bottom of the cup. And as we add more and more sand and more sugar, then that's going to get more and more concentrated. So over time, we're going to need to do something to address the concentration of both the sand and the sugar. So the sand, well, that's an example of the heavier minerals and particulate that is going to settle towards the bottom of the steam boiler. And we need to get rid of that sludge, that particulate, because if we don't, it's going to back up and it's going to occupy too much of the boiler space. So we address that by opening the bottom blowdown valve that we've spoken about previously. And if we're generating steam at a nice high pressure, 10 bar gauge, any pressure drop across the blowdown valve, that's going to result in a mass of water dragging that particulate to waste. We then close the valve. The level control probes will have registered that that water level's fallen, and we'll be able to recover and start generating steam again after a short delay. Typically, we perform that blowdown function every 8 hours with the valve being open for 2 or 3 seconds. But that's all well and good. That will only address the sand in the analogy of the cup of tea I was talking about. If we want to address the TDS, the total dissolved solids, so the sugar in our example, then we can only do that by dilution. So we take a sample of the water from the side of the boiler, where it's going to be representative of the entirety of the concentration of the water in the boiler. We cool that sample and we test that sample for conductivity. If it reaches a high conductivity, well, it's indicative of a high concentration of TDS in parts per million. We simply open that valve. We bleed a certain mass of high concentration water to waste. As the water level falls, the level control probes call for a similar mass of water at a much lower concentration from the feed tank. So we've addressed that high concentration by dilution. Now, the reason that that's important is if we allow the TDS level to remain at too high a point, the concentration means that we're going to get a lot of foaming on the surface of the boiler water. And that makes it really difficult for the level control probes to have an accurate understanding of the precise water level within the boiler. It also means if we get a lot of foaming within the boiler, it's likely to be an indication that we've got scaling of sensitive areas, a barrier to heat transfer, if you like. But if we get a fluctuation in pressure, it also means that that foaming layer can expand and we can draw a significant amount of foam into the header. And that foam's going to be very wet and sticky. So that's what's going to contribute to that wet steam that we were speaking about with very little energy in it. And over time, that foam's going to dry out as scale. And that scale will be conveyed towards the process where if we're using the steam for heat transfer purposes, the scale is going to create a barrier to heat transfer. But if we're using that steam for direct injection purposes, well, it means that ultimately we're going to have a concentration of dried out boiler chemicals in the form of that scale entering into that process or atmosphere. So it's important to address the TDS level in terms of part per million, and the boiler manufacturer would typically give guidance on that. It could be anywhere between 2,500 and 3,500 parts per million concentration, depending upon what the boiler manufacturer stipulates. The risk of blowing down too much or too often is, well, it's a waste of energy. But if we fail to blow down often enough, then we're going to have a problem with that scaling. Now, the bottom blowdown valve, we can operate that manually, or we can operate it on a timed actuator. And similarly, with the TDS control, we can either blow that down manually, or we can blow that down on an actuator that is taking a conductivity reading from the side of the boiler. The benefit of moving away from a manual blowdown system to an automatic blowdown system is essentially that we're ensuring the blowdown is kept at the prescribed rate. So that's important for a number of reasons. First of all, it means we're minimizing the risk of that foam being carried out into the header, resulting in scale. It means that we're ensuring that we've not got an unnecessary loss of energy. But it also means that we're putting in the absolute minimum of feed water into an operating boiler, meaning we don't get that recondensing effect in the steam space, which in turn means that we're not producing wet steam from time to time. And as we can very easily upgrade and retrofit new modulating pumps and more sophisticated level control probes, we can very easily move away from a manual to an automated blowdown system. And I just want to show a couple of quick stills that some of you may have seen from the links to the various YouTube channels that we show. Over towards the left-hand side of the screen, you can see what we mean when we get carryover. So if we get a sudden fall in water pressure within the boiler, you can see that that's likely to result in a little spiral of moisture, of water being drawn into the header. And that's going to contribute to that wet steam. And over towards the right-hand side of the screen, well, that's a still of that foaming layer expanding as we get a pressure drop in the boiler. And that really demonstrates what can cause that steam contamination that we spoke about. So more sophisticated processes, especially in the food, beverage, pharmaceutical, healthcare sector, they're moving away from that hot well that we spoke about. And they now appreciate that by being able to hold the water under pressure, we can elevate the temperature to 100 degrees and slightly above, because we're not at risk of causing cavitation of those feed pumps. And that in turn means we've purged off a lot of the air and the non-condensable gases. So the benefit to that is, well, we need to add far, far fewer boiler chemicals whenever we're using a pressurized deaerator. And if we're adding fewer boiler chemicals, then we get fewer contaminants present in the steam itself. We get less corrosion of the steam boiler, of the distribution pipework. We get less foaming because we're adding fewer chemicals, and we need to perform less blowdown. So there's an energy cost saving. And ultimately, it means that we're keeping the steam drier because we're not having that quenching effect by continually adding colder water into an already warm steam boiler. We get a consistently better condition of steam with a pressurized deaerator. So it's only by ensuring that we're treating the raw water correctly and generating the steam correctly that we can ensure that we've got a good condition of steam that leaves the boiler house and enters the steam distribution network. But you'll hopefully remember that we've got to observe good working practice to get the steam from the boiler house to the process so it doesn't degrade along the way. So remember, when we're talking about a good condition of steam, actually in the distribution pipework itself, not at the process, but in the pipework, we're talking about ensuring that the steam is as dry as possible. So we can do that by removing the condensate across those steam traps. We're going to want to keep the steam clean of particulate. So we need to protect vital components with those Y-type strainers. We want to vent the air away so it doesn't become entrained within the steam and carried to the process. But of course, we're going to need to ensure that the steam pipes are sized correctly. And we've spoken previously about pipe sizing. And the reason that accurate pipe sizing is important whenever we're talking about the quality of the steam is, well, if we've oversized the steam pipes, then we've got a greater heat transfer surface area than we may otherwise need. So we're encouraging more of the steam to condense out in the distribution network. And if we're doing that, then we've got more condensate. We're putting ourselves at risk of encountering more corrosion and more erosion. And we're also encouraging the steam that is being produced to further degrade as it travels across that trapped mass of condensate. So we also need to remember the first principles that steam is ultimately a gas. But when steam gives up its heat energy, it condenses. And at that point, that condensate is a liquid. So we need to ensure that we're observing that good working practice to get the condensate to the low point where it can be trapped and removed. It's only by doing that that we can ensure that we're keeping the steam at its driest possible condition. Those design considerations, such as ensuring that any trapped condensate can drain to a low point under gravity, at which point the steam trap can take it away, and ensuring that we're taking the dry, saturated steam from the pipework at the top, where it's going to be at its driest and where we're not at risk of flooding the process with that liquid condensate. Remember, condensate, it doesn't have anywhere near as much heat energy present within it as the process will be expecting. We've also spoken about air venting. We want to ensure that we're venting the air away. Now, we treat the feed water with boiler chemicals to ensure that we're polishing off the air and the non-condensable gases. That's to protect the boiler from corrosion. In the distribution pipework itself, we're always going to have air present because when steam condenses and pulls a vacuum, it can draw in air in through vacuum breakers and valve spindles and gaskets. But what we need to do is ensure that once the steam system is pressurized, that steam pressure can push the air out across a little air vent. And it's important to ensure that we use a thermostatic air vent because a mechanical air vent, it simply wouldn't work because condensate and steam have got the same temperature. They've got the same, they've got condensate can exist at a different density to air. So we need to ensure that the air can be vented away thermostatically because it exists at a colder temperature to the steam. And that's really got its basis in the understanding of Dalton's law of partial pressures. In layman's terms, think of that mass of air really diluting the temperature that is present in the steam. So in other words, it can cause the process to slow down significantly. So we want to vent the air away from the steam system at the very, very end of the distribution network, but also at other areas such as the occasional high point. And the purpose of observing that good working practice that we've gone through previously is to ensure that not only are we generating steam efficiently and at the best possible condition, we're distributing it in the best possible condition with a view to getting it so that it can be utilized at the process in the best possible condition. And as we've mentioned previously, we can be using the steam in different ways. We could be using it in a closed loop heat exchanger, such as a plate or a shell and tube heat exchanger, or a coil in an air handling unit. And when we're talking about steam quality under those circumstances, remember it's dry steam, free of air, with very little particulate entrained within it. That's what's going to be important. But whenever we're moving towards using the steam for direct injection, that's when we want to measure the condition of the steam. And that's when certain engineers on our client's site will refer to the steam condition and they'll benchmark it against those BS EN 285 standards. So we've spoken previously about the purpose of a steam separator. So a steam separator's really got three main benefits. And we use a steam separator, first of all, to remove any entrained moisture. And if we've sized and selected a separator correctly, it can hit that 95% dryness target. So by removing the entrained moisture, we've kept the heat content of the steam as high as possible. But whenever we're using steam for direct injection purposes, it also means that we've reduced the contamination that an excess of moisture and boiler chemicals can cause. I said reduced there, not eliminated. But a third benefit is, well, entrained moisture can also create erosion of sensitive areas, such as those control valves or pressure reducing valve seats that we've spoken about previously. And just going back to control valves, if we do get erosion of control valves or pressure reducing valves, that abrasive nature of a metal to metal seat, it means it makes it highly unlikely that we'll be able to accurately regulate the exact mass of energy that is delivered to the process. So we may wrongly assume that there's a problem with the heat exchanger or a problem with the control valve, and it could simply be that we've either sized the control valve incorrectly or we failed to condition the steam that's passing across the control valve, because that could ultimately be causing the problem that is impacting on the process. So we always size a control valve in accordance with the mass flow rate of steam required. So we spoke earlier about the impact that wet steam can have on a process. And the equation above that you may remember from the heat exchange presentation we went through, I think it was 4 weeks ago now. Well, this shows us how we can calculate the heat requirement of a plate heat exchanger if we know two things. We need to know the mass flow rate of steam that's being delivered onto the heat exchanger, and we need to know the latent heat that is present within the steam, which we can get from the steam tables if we know the steam pressure. But remember, this equation is based on the understanding that the steam is fully dry and saturated with energy. So using the example from the steam tables that you can see above, you can see on the bottom of the two graphs at the right-hand side of the page, it really demonstrates that if we've got very, very wet steam, for example, steam that is 50% dry, well, it really demonstrates that if it's 50% dry, it's 50% wet. Therefore, we've got 50% of the latent heat energy that the process requires. So the reason that's going to cause us a problem is, well, it means that the process is going to slow down significantly. It means that the heat exchanger could be significantly undersized, or that we may fail to hit the required target temperature. But that problem extends significantly if we've then got a mass of air or other non-condensable gases mixed in with that wet steam. We've got less energy and we've got a barrier to heat exchange as well, which explains why it's so important not only to condition the steam with a separator, but also to vent that air away. So I also want to talk about condensate as well, because we've mentioned that when steam gives up its heat energy, it condenses. And when we're using steam for direct injection, that condensate goes into the process. But whenever we're using steam in a closed loop system, such as a plate heat exchanger, we need to give thought to removing the condensate at the appropriate rate. Because if we're not doing that, the condensate as a liquid with far, far less energy on it, that can occupy a lot of the heat transfer space and cause the process to slow down. So we could be pointing the finger of blame at the steam quality, when in actual fact, there's nothing wrong with the steam. It's just the condensate isn't letting the steam into the heat exchanger where it can do its job. So moving forward to look at a couple of processes, we can look at a boiling pan or a jacketed vessel in the food and beverage sector. And you can appreciate that venting that air away and getting rid of that condensate is critical in letting the steam do its work. Other applications, such as retorts in the food and beverage sector, they are going to have exactly the same issues. We're going to need to vent the air away, and we're going to need to remove the condensate on top of ensuring that the steam is of a significant condition. So whenever we're encountering a steam system, one of the first things we want to ask ourselves is the steam likely to contaminate an atmosphere or a process? Is it an ingredient, in other words? Is it likely to cause contamination? And if the answer to that is yes, then plant steam simply isn't going to cut it. It's not good enough for our requirements. We need to go back to the steam condition triangle, and we need to apply a HACCP, really. And if we want to minimize the risk of contamination, the only way we can do that is by moving above the red line and generating what we refer to as clean steam or chemical-free steam. Now, a definition of chemical-free steam is steam that is generated using a chemical-free source of water. It could be RO water, for example. And we use a stainless steel generator, which is essentially a 316 stainless steel vessel with a 316 stainless steel coil running through it. We can use plant steam to raise that chemical-free source of water to the point where it is going to generate clean steam. And if we then distribute that clean steam a very, very short distance from the generator to the point of consumption, well, we're ensuring that the steam won't deteriorate, and we can guarantee that we can hit the requirements of EN 285. So I'm just going to very quickly show you an animation of a typical clean steam generator. So hopefully you can appreciate the benefits for a lot of our clients in using clean steam generation, because it helps them ensure that they can hit the requirements detailed by EN 285. And typically a clean steam generator would be located as close to the point of use as possible to ensure that that steam does not degrade in any way as it travels from the point of generation to the point of use. Other terminology that clients on a steam using site may use is steam purity. And the difference between steam quality and steam purity is steam quality is usually the physical properties of the steam, the temperature, the pressure, the dryness. Whereas when we're talking about steam purity, it's what's entrained within it. And Different processes are going to have different purity requirements, but typically purity is tested by taking a condensed sample of the steam and putting conductivity probes across it. That's going to tell us the part per million of likelihood of any contamination within that sample, and different processors are going to set their own values of what is acceptable and what isn't. But for those of you that may work from time to time in the food and beverage sector, there's another standard that is very often overlooked, and that's EC 1935-2004, which basically dictates that anything that comes into contact with a food product needs to be compliant with this very standard. And of course, if we're using steam for sterilizing that baby food jar, or being able to squirt across a jam jar to pull a vacuum when the steam volume collapses and condenses, well, by nature, that steam, and therefore the steam generator, does need to be EN 1935-2004 compliant, which the little clean steam generator that I showed in the previous animation is. And something else that's quite often overlooked, as we've mentioned the importance of removing the condensate from the distribution pipework and the process. And that's principally the benefit that we understand in doing that is obviously recovering as much of the energy as we possibly can. That's something that we've spoken about previously. But if we're not getting the condensate away at the appropriate rate, it can impact the process because it can flood the heat exchanger. So it's critically important to ensure that we've sized and selected the correct type of steam trap. Now, in the previous presentations we've gone through, we've looked at steam trapping on plant steam systems, where we understand that there are 3 different types of steam trap that we can utilize. They've all got the benefits and the drawbacks, and they need to be selected in accordance with the specific nature of each individual application that we're looking at. However, when we're moving away from a plant steam system, and when we're looking specifically at the clean steam system, remember, we want to ensure that the steam arrives at the process hitting that EN 285 95% dry value. We're going to need to ensure that we're draining the condensate away very, very quickly. So the only trap type that is acceptable for us to use on a clean steam system is a thermostatic trap. And as you can see down at the bottom, a little thermostatic trap, if it's got an element that operates at a temperature that is very, very close to steam, it's going to let that condensate pass as soon as it forms. It also means that if that trap fails in the open position, it means that we can guarantee that we're never running the risk that that condensate is at a risk of backing up, and ensuring that that 95% dryness value set by EN285 is not achievable. You'll also notice that we don't have that dirt pocket that we've spoken about on a plant steam system. The reason being, well, if we're generating chemical-free steam and distributing it in 316 stainless pipework, there isn't going to be any particulate to remove. So we've typically got a straight through configuration to allow the condensate to pass through the trap very, very quickly. And just a little bit more about the condensate. We've spoken previously about ensuring that we may need to pump the condensate away from the heat exchanger itself. And certainly there are going to be occasions where we need to pump the condensate back to the boiler house using either a mechanical condensate recovery pump or an electrical condensate recovery pump. So why is that relevant when we're talking about steam condition? Well, do you remember right back at the start of the presentation, we mentioned that condensate has already been chemically conditioned. It's in an excellent state for going back into the boiler. The more condensate we recover, the less raw water we need to use to make up those losses. The less raw water we're consuming, the fewer chemicals we're adding to the hot well. The less foaming we're going to have, the less scale we're going to have entrained within the boiler chemicals. It also means that if we're adding fewer chemicals into the boiler, the less blowdown we've got to perform, and the reduced likelihood that we're then going to have that steam condensing in the steam boiler, resulting in that wet steam. So you can appreciate that if we're talking about the steam condition and keeping the condition and the quality of the steam as high as possible, there's a value to considering what happens on the condensate side of the system as well. And we also know that from time to time, we're going to have flash steam venting away from places such as the vent at the top of the condensate receiver. And we should remember that if we've got a significant pressure drop, then we're able to calculate exactly how much flash steam is vented away and being lost to atmosphere. And we can see over towards the right-hand side of the screen the reasons why that is. If we don't vent that flash steam away, it's going to exist at too great a volume in the condensate pipework that's been designed to accommodate a much smaller volume liquid. So we need to engineer everything we possibly can do to either reuse that flash steam at another process, or to condense as much of that flash steam as we can before it's vented to atmosphere. So for example, if we're using an exhaust vapor condenser, as you can see on the screen here, we're condensing a significant percentage of that flash steam, and we're returning that condensate back to the receiver so that we're keeping the condensate losses to a minimum, and we're ensuring that the steam condition can remain consistently high. But we also know that there are a very, very small number of applications that may have traditionally dumped the condensate to waste for fear of it being contaminated in some way. And we no longer need to do that for reasons that we've mentioned. For one, there's a significant amount of energy in condensate. And for two, the more condensate we can recover, the better the steam condition typically is. So if there's a fear that the condensate could be contaminated, there's no reason why we can't put conductivity probes or turbidity probes upstream of a diverter valve that dumps condensate to waste when it's not fit for reuse, but when it is, it diverts it back to the boiler house. It means that we can ensure that we're safeguarding not only an efficient, but also that a consistently good condition of steam is going to be generated. So there's a lot to think about there, and I'd just like to summarize very quickly. The first thing we need to think about is the condition of the water that we're using, regardless of whether it's a plant steam system or a clean steam generator. If we put a poor condition of steam into a clean steam generator, we're not going to get clean steam. If we put very poor water into a plant steam boiler, we're not going to get good condition of steam. We also want to think about whether the steam's fit for purpose or not. Is the steam likely to contaminate an application? If so, we want to refer back to that steam condition triangle and do everything we can to protect against that risk of contamination. Going back to those boiler controls, automating the TDS and the bottom blowdown, moving towards a modulating pump, increasing the sophistication of the level controls, that will have a positive impact, not only on energy efficiency, but also on steam quality. Think about the risk that contamination of condensate can pose to a process. But also, as with all things, it comes back to the basics. And think about the impact that wet steam and an excess of air can have on the process. So thank you very much for bearing with me once again. That concludes the sixth of our series of presentations that we've got planned for you over the coming months. We've got the topic of energy in steam, and then we're going to have a nod to the future on the 10th of March. But as with all things, if there is any appetite for any more education, we'd be more than happy to provide formal training. You can see the details by referring to our own website. But as previously, please don't hesitate to contact with me on LinkedIn, email me if you've got any questions that we don't have time for addressing tonight. And please also send me an email or a message if you'd like a PDF copy of the slide pack or an attendance certificate sending over. Thank you. Brian.
Right, thanks, Dan. As always, great job. So thanks very much. I've had a couple of questions that have come in. So first one is, if time permits, can we ask Dan, what methods are used to figure out the amount of scaling, corrosion inside steam carrying pipes?
Corrosion inside the pipework itself?
Yeah.
Good question. It's a difficult one to answer that. A camera would be the obvious one that whenever we're able to take the pipework apart. But usually you can get an indication for the amount of corrosion and scaling by observing the baskets of any Y-type strainer on a regular basis. That would generally give you an indication of the overall health of the pipework itself.
Yeah. And follow-on questions, how do engineers determine whether the piping has reached the end of its life? I guess is the same answer.
Yeah. Any pinholing of pipework, any erosion of sensitive areas caused by corrosion that's conveyed in the steam, the condition of the condensate itself. Have a look at the condensate as it travels back to the boiler house. You can see if there's anything entrained within it, any scale, the color of it, and so forth. But it all comes back to ensuring that the water treatment regime in the boiler house is on point as well.
We did get a comment that came in from somebody just prompting NDT testing, which is where my thinking might be, but it's probably not going to be an exact science because scaling might, I don't know whether you'd pick scaling up with NDT.
If it's scaling that's deposited on the pipework, you would, but not scale that is conveyed in the steam. That's the danger.
Yeah.
And it comes down to ensuring that we're observing good working practice and we're ensuring that the water treatment is on point and that we're generating steam efficiently. They will all have a positive impact, but if any of those things, if any of those points are dropped for any reason at any point, then we could be living with the consequences for quite a while.
Yeah, and I think during changes to systems and maintenance, if you take care to notice the condition of the pipes when you break them, it's going to be another indicator, isn't it?
Absolutely.
So next question is, so how do you prevent the blowdown function with the sludge and sediment from damaging the valve or corroding it?
It's a large bore valve, typically. It's a large bore cast steel or stainless steel valve that sits on the bottom of the boiler.
So it's specifically designed for the purpose. Is that the? Yeah.
And it's if we're looking at the TDS at the side of the boiler, if it's it is an automated valve, but it is specifically designed for this purpose because it's an on-off valve rather than a modulating valve. So it needs to be. We need to ensure that we're not exposing it to too much erosion, and for that reason, it's been specifically designed for these pressure drops and these purposes.
Okay. Further comment about NDT. Scale means there is missing metal somewhere, so NDT would likely pick this up. So.
Yeah. I mean, you'd hope so, but of course, the scaling, it can also be mineral scaling. It can also be as a result of the boiler chemicals. And again, it goes back to the point that we need to ensure that the water chemistry is kept on point and it is periodically examined to make sure that nothing in the raw water quality or nothing in the dosing pumps has caused a change to that.
Okay, last question. Why do boilers have a direct opening for steam to rise up through, which, as you mentioned, could allow water being sucked up in a spiral? Do they ever have different shapes of entry to the pipes to minimize this uptake?
Yeah, I mean, different boiler manufacturers are going to have a different design of offtakes. Yeah, like a series of baffles, if you like, to ensure that the water is separated wherever it possibly can be, but it's impossible to guarantee dry steam. without causing too much of a resistance. So one of the first things we always recommend, and the vast majority of boiler manufacturers recommend, is straight after the crown valve, there should be a steam separator. And that steam separator should be sized on a worst case scenario assumption that the steam could be 25% wet. So if the boiler's been sized on a 10,000 kilogram per hour, that separator needs to be sized to remove 2,500 kilograms per hour of moisture, of condensate, in other words. That's to ensure that the steam is at the best possible condition before it enters the distribution network.
Okay, thanks for that, Dan. There's no more questions in, so just to close the show this evening, just to remind everybody, thank you, Dan, for pointing out, it is a centenary year for the Yorkshire region, which was the first region set up by the IMechE outside of London. So it's 100 years old this month, and there's a couple of events planned in coming weeks and months to celebrate that. Big thank you to the IMechE volunteers, Nikki Baxter, who does all the back office stuff and handles the invites. As always, Dan, a big thank you to yourself and Spirax Sarco for supporting this, and a thank you to Project Solutions, my boss, for sponsoring or hosting the event this evening. Next one's a fortnight's time. What's the subject, Dan? Just remind me.
We're looking at energy and steam. So we're looking at how we use the energy in the steam. We're looking at the benefits of steam compared to other sources of heat energy. Okay,
that's brilliant. So have a nice evening, ladies and gentlemen, and we'll speak to you in a fortnight's time. And thanks, Dan. Cheers now.
Not at all. Thank you very much. Thank you.
Cheers.